Hi everyone, welcome to this class where we are going to discuss the very interesting topic of maxima and minima, and I'm going to explain it in a very simple way. I'll show you the graphs and the meaning of this topic, not just the formula. So keep your pen and paper ready and let's begin. Before we get started, just a quick reminder, do check out the courses on our website manochaacademy.com and our Android app Manocha Academy. All the links are given below and please do share it out with your friends as well. So we are going to discuss the topic of maxima and minima. Maxima means maximum value, right? And minima means the minimum value. So for example, if I give you a function like this, function means if you give it an input x, it gives you an output which we plot on this graph, right? Where the function is plotted like this, y against x. So this is my function fx over here. So based on this graph, can you guys tell me where is the maximum value of the function, the maxima? So it's pretty easy to see in the graph. This point is going to be the maximum value. So basically you are looking for that top of the hill, right? You're looking for the top of the hill. So do you guys agree with me that this point, this is the maxima of the function and the maximum value here, and we can say it is happening at the function gets its maximum value at a certain point. Let's call it c. C can have any value, 2, 3, whatever, right? So this is the function gets its maxima at c, and this maximum value will be what? You plug in c into the function. So this value here will be what? fc. So this we can say is the maxima here. At the point c, and we can read the value from the y-axis. This is on the x-axis. At the point c means you're reading the value at the x-axis. Suppose at x equal to 2, and then whatever the value is there, f of c is the maxima. Clear? Now moving on to minima. If I give you this graph, once again we have plotted the function y equal to fx. This is our function, right? Y on the y versus x axis. So where is the minima of the function? Pretty simple. You can see this, the lowest point, right? Minima means where the function takes on its minimum value. So see, it's basically you're looking for that valley, the bottom of the valley. Okay, so this is clearly the minima, the min point, this one. And where does it occur? Once again, you'll take this minimum point and you will, trace it to the x value over here, and we can say it occurs at the point c. Okay, and what will be its minimum value? Once again, you read it from here. At c, the value fc. So simple. This is the meaning of maxima and minima, right? Remember, maxima is the top of the hill, top of the hill. So you can remember with that analogy, maxima is the top of the hill, and minima is the bottom of the valley, bottom of your valley. This is the valley, that's the bottom. Now in maths, when you read the formal definition in the book, it will look something like this. So you have some function, right? Function is defined on some interval. Interval means you're considering some domain or some input, range of inputs, and in that interval I, you're considering some point. So when do you get the maximum? That point c. Remember, we looked at this point c. At this point c, what is special about point c? The value of the function fc is the highest value, and that means the fc is greater than all the fx. If you compare all the fx at the other points, fc is the maximum. So see, fc is greater than all the fx for all x. This inverted a means for all x that you're considering, let's say in this interval from here to here. Okay, so that is called the c is the point of the maximum where the function takes on the maximum, and fc is the maximum value. Similarly, same thing for the minima. You can see the minima is happening here at the point c over here, and the minimum value is f of c. So what is the condition? That this f of c must be lesser than all the fx. So compared to all the fx, this is the lowest value, right? And that's why we call it the point of minima. So this is the formal way of writing it in the book. Now if I give you this graph, and I say, let's say this is our function once again. This is our function fx, and we can talk about this interval. Let's say this is a interval here. So we are considering this interval, and this interval that we have, let's take it to be the closed interval from a to b. Okay, so that means including a is included and b is also included. Now guys, can you tell me what is the maxima minima here? What is the maxima minima here? So if you take a look at it, maxima minima in the basic sense, maxima means the highest value, minima means the lowest value. So obviously if you look at this graph, you can see very easily that this is clearly this point is clearly the minimum. So I can write min over here or minima. And this point, clearly, do you guys agree? This is the maximum value. We can write here maxima. Yes. So we can say the minima occurs at A. The minima occurs at A. So this is where the minima is. And the value you can read off from here. This will be the minima value. And similarly, same thing. The maxima occurs at B. And we can read it off from here. Right? We can read off the maxima value from here. Got it? So in this closed interval, it's very clear. So here maybe that hill valley will not help because there's no hill value. It's just a simple function, right? It's increasing like this, and there's clearly the minimum point, the maximum point. One important thing is, and we'll talk about that, this interval needs to be closed. That means A and B are also included, right? And so we can say that clearly here the extreme points are the minimum and maximum. If it was the reverse, if it was going down like this, it would have been the reverse. This would have been the maxima. This side would have been the minima. Yeah. Now, why are we learning all this? So, before we dive into more mathematical details, what are the uses? What are the uses of maxima and minima? So, one is it will help you to draw the graph of certain functions. What do we mean by that? Like suppose you know a certain function, as an example, suppose you know a certain function. Let's say it's a quadratic function, right? Quadratic function, we know the graphs are this curve kind of ones, curve graphs. And suppose I tell you that, hey, this quadratic function takes on a maximum value, let's say at x equal to 5. And its maximum value you have calculated is, let's say the value 4. Then how can you draw the graph? Because it takes on its maximum, that means the graph, you know, will be, suppose, curving like this. So see, it will help you draw the graphs. Suppose I give you the minimum also, maybe you can curve it up again after that. So it helps to knowing these points of the curves, the turns, maxima, minima is the turning points, right? It really helps because you can see maxima, minima, when in the hill valley, it is the turning points. So that can help you draw the graphs. Another nice application, real life application is, suppose a company, you know, these companies, the goal of the company always is to maximize the profit. Okay, let's say it's a manufacturing company manufacturing certain whatever, certain article, right? Some product it's manufacturing. Let's say it makes X number of items, and its profit they've calculated. They've done the maths. You know, all the selling price minus cost price and all those things. They have taken into account all the accounting they've done. And they have arrived at this profit function where x is the number of items, and it turns out to be, you know, ax plus bx square plus c, right? Some function like this, or ax square plus bx plus c, whatever, right? Some function they have got where x is the number of items produced. Now here I want to maximize the profit, so that means for this function I want to find its maxima. So I want to know that how many items should we ideally produce, let's say in a day or in a month, to maximize our profit. Okay, so this is where you want to find the maxima of this profit function. See, that is the use of it. Clear? Another way is that, you know, suppose a ball is thrown in air, right? If we throw a ball in air and we want to find the maximum height. So once again, you know, you may say I'll use simple equations of motion that I've learned in physics, but let's say there's friction involved and you know the equation that you get is more complicated, or even if it's that equation, right, whatever equation you get about the height, once again it becomes a function and you want to find its maximum. Or another, military example is, suppose there's an enemy helicopter or plane is flying and they have calculated its function. They know its, they know its path. So let's say the helicopter's path is something like this. So here's a helicopter. I'm not a great artist, but there's your helicopter, and you can see that, let's say it's flying and it is following a, let's say a parabolic or some curved path like this, and they have actually worked out the function, right? Let's say this is the x-axis and this is the y-axis. They've worked out the function. So if they want to shoot it down, right, or let's say they have some short range missile to shoot it down, maybe if it's too high they can't shoot it down, but if the helicopter is at its lowest point, it is easiest. So I want to shoot it at its lowest point, nearest point. That means what am I looking for? What am I looking for? The minima of this function. We are looking for its minima. So see, there are military uses also of maxima minima. Lots of uses in profits, companies, everywhere this topic is used, and very, very important topic. And that's what we are going to learn, that for any function, how do we calculate the maxima minima? So let's look at some important points that we talked about, that let's say a function has an extreme value, right? If it is an extreme value in this interval, so we were always think in terms of a function, right? Some function is given to you and they're saying it has some extreme value in that interval. That means it has either a minimum or a maximum, right? It may go up. So in a certain interval a to b, let's say it's given to us, maybe the function is like this. So this one, the maxima can also be called its extreme highest value, right? Or it could be a minima kind of function, this kind of function in this interval. So then clearly this is the extreme, which is the minima, right? This is the extreme value. So if a function is having an extreme in an interval, then it must be having at least one minima or maxima. So that's just a simple point. Now here, if I tell you every continuous function on a closed interval, it has to have a minima and maxima, right? You look at any of these examples, see these curved examples, clearly this one has a minima. This curve has clearly got a minimum value, right? If the curve was upwards, it would have a maximum value. And we also saw the other case, if it is a straight line like this, right? If it's a straight line, then also it will have something, right? Or if it's a curve like this, in this interval, as long as one important point is the interval is closed. Closed means A and B are included, and we'll talk about that why. Because if it's open interval, then you don't know which point, where to stop your test, right? How will you get your maxima minima? So here we are talking about in a closed interval. If you fix your A and B, let's say from 2 to 5, right? Then every continuous function, for any continuous function means there is no sudden jerk, right? Smooth kind of function. So every smooth function, any graph I draw for you, this one, any graph that I draw, any graph, you will always get some maximum, you can find some minimum value. Or even if it's a flat line is an extreme case where both maxima minima is equal to the constant value. So any of these graphs, right? So let's just draw the general case here. So if we take any continuous function from A to B, something like this, or whatever function you're taking, you can always work out. Do you guys believe and agree with me that you can always work out its maximum or minimum value? That's what this point is telling. Okay. And the last point, every monotonic function has its minimum and maximum values at the endpoints. Do you guys know what is the meaning of monotonic function? Monotonic function means it is either continuously increasing or continuously decreasing. Every monotonic function. So monotonic function means either continuously increasing, so continuously increasing, or continuously decreasing. So like for example, see, look at this monotonic function, it is an increasing function, and we already looked at this example. So where will its minima or maxima be? It's going to be at the endpoints. This is its minimum, that is its maximum. Clear? This makes sense? So this is clearly its minimum value, and that side is the maximum value. And see, minimum, maximum, automatically we know. The special thing is it will happen at the end points, the extreme points, because it is monotonically increasing. And if you take the other example also, if you take decreasing function, then again see, at the extreme points of this closed interval, it will be the opposite this time. This is going to be the minima and this side will be the maximum. Once again, clearly happening at the final, the extreme endpoints, as you can see here. Now if I give you this question, find the maximum and minimum values, if any, for this function y equal to x square. So we've got two parts where they are giving us the x that you need to consider is all real numbers, right? Basically the entire number line. So I've given you the function, and to make it easy for you, I've sketched it out for you also, right? You can sketch it out. So this is the function here. It's the x square function, simple, right? And you can see x square is always positive, so there is no negative value of x square. It's square of a number, right? So this is our function y equal to x square. This is the function clearly, okay? Now you tell me, just looking at this graph, what is its minimum? Just graphically, right? We'll come to the mathematical, the calculus part. Just looking at its graph, it's very easy. You can tell me what is the maximum minimum value for all real numbers. So clearly it is having the bottom of the valley is right there. So we can clearly see that this is going to be the minima. Yes, this point is basically our minima. So for part A, we can confidently write that for y equal to x square, where x belongs to R, that's written there in the question. So basically the minima is going to be where? At x equal to 0. The minima is at x equal to 0. Do you guys agree? The minima is happening at x equal to 0. And what is the minimum value? What is the minimum value? So they are asking you for the value, not just the position. So at x equal to 0, the minimum value will be 0 square, which you can see directly from the graph, 0. Simple. This is very easy. Now, what about the maximum value? Tell me guys, what will be the maximum value for this x belongs to R? So clearly you can see the function just goes on increasing. So as I keep increasing, right, it will keep going on and on and on. So if I give it bigger and bigger numbers, it will give me a bigger answer. And x equal to real is an open interval, right? I can go up till infinity, but infinity is not a number, right? It's just a concept. Any large number you can keep on, like you say infinity plus 1 is again infinity. So here we don't say you can say maxima is infinity, but we say basically it doesn't have a maxima. It just goes on increasing, but it clearly has a minima. This is very important point, that for in x equal to R does not have a maxima or no maxima. There is no clear highest point. Okay? But now let's look at part B, and then you will understand the concept. I am explaining it in a very simple way with examples. Look at this. If I tell you, no, don't consider the entire number line. I want you to restrict yourself to this interval. And you can see it is a closed interval. Closed interval means including the endpoints. And you know from the square brackets. Otherwise open interval means with the open bracket, right? So this is with the closed bracket, square brackets. So I want you to go from minus 3 to 3. Now you tell me. So minus 3 to 3 means from here to here. Minus 3 to 3. Now you guys tell me, what will be the maxima minima? So in this interval, so in minus 3 to 3, this second part, now again minima is very clear. Minima is at x equal to 0 and min value is 0. 0 square, that is pretty clear, same thing, right? Now you guys tell me what will be the maxima, tell me. So maxima, where does it happen? So if you look at the this two endpoints, the 3 and minus 3, can you see that is where it is highest? Okay, and it is highest at both the points. So maxima is happening at x equal to, look at it, 3 and minus 3. And what is the maximum value? Not 3, 3 square. See, the function is x square. The input is 3, the output is 3 square. So we can say the max value is equal to 3 square or minus 3 square, which is basically equal to 9 is the answer. So see, this is what I was telling, that important point, that if you close your interval, right, it's almost like if you close the door, okay, like the teacher closes the door and says no more children entering, can I find the maximum age of this classroom and the minimum age, right, or maximum height, minimum height? Yes, because the door is closed, the interval is closed, right? It's not like suddenly one more student, a taller student or a shorter student walks in. No. So once the interval is closed, right, then we can definitely talk about the highest and the lowest, right, the maxima and the minima. And in this case, the answer came out to be, for this example, at 3 and minus 3. That's where the graph reached its highest value, and the value came out to be, so let's say this is the highest value, and it came out to be 9. Let's take a look at another example. Find the maximum and minimum values, if any, of this function. Let's say I've given you this function fx equal to x, where x belongs to 0 to 1, okay, 0 to 1, and now notice that this open bracket means it's an open interval, okay. Let's understand the meaning of this. Let's understand with depth, right. So here you can see that this is clearly an open interval, okay, and in part B we have a closed interval, so we'll see both the cases, okay. So the function given to me is fx equal to x, and I've plotted it for you, right. It's basically going to be this linear function where every value of y is equal to the x value, right, fx equal to x, this is our function, okay. And you can see that I've kept these open circles at the end. Can you see the open circles? Because it is a open interval. Now the question is, what is its lowest and highest value? So you may be tempted to look at this graph and say, okay, the lowest value is 0, highest value is 1. Well, the answer is wrong. Why? See, it's an open interval. So 0 is not included, okay. Now I'll say, okay, then what is its minimum value? You will say, sir, it's 0.001. I'll say, don't think so small, go a little lower, 0.000001. You'll say, right? I'll say, no, you need to go a little lower, 0.000000001. I'll say, no, wrong answer. You'll go even smaller. So where will you stop? 0.0000000. It's an open interval. You don't know where to stop. That's the problem, right? So that is the problem here. We don't know where to end our search. Same way at the highest. What is the highest of this? 0.99, 0.999999, 0.99999999. Where do I stop? Right? So that is why open interval. Get the concept clear. Open interval, very, very important. No maxima, minima. No maxima or minima here defined. So it is possible you may not be able to tell a maxima or minima, because what will be the value? Yes, it is approximately 0, 1. No, but in maths we want the value, okay. But if you close the interval, how do we represent a closed interval? The difference is, now we will draw a solid circle, not a empty, not a hollow circle like that. We will draw a solid circle, okay. Now we can confidently say that because 0 is included, it is very clear that the minimum value will happen at x equal to 0, okay, and the value also happens to be 0 because the function is fx equal to x, and the maximum value, guys, is right here, okay. So this is very clear that when it is closed interval, then the minimum value, I was using pink color there. So the minimum value, minima is at x equal to 0 and f0 is 0. So that's the answer. Similarly, maxima, clearly defined. So maxima is at x equal to 1 and f of 1 is 1. There you go. So moral of the story, closed interval, defined. Open interval, you can't say the the maxima minima, right, for this function. So yes, we can use the calculus concept of h tending to 0 or h tending to 1, but I want the value, right? We can't say that, right? So we'll look at what to do in open intervals, but for this case that we were looking for, what is the final absolute, the maxima or minima, we can't give a value, right? Logically, I'm going logically, not just theoretically from the book. If you logically think, right, this is the answer, and this is what the book says also. So now let's come to the concept of local and absolute maxima minima. Okay, what do we mean by this? So now some more interesting terms, and you can see I've got a more interesting graph over here, which is not just a simple highest and lowest. It has multiple things, right? It has multiple things, or you can think of a sine graph or cos graph in trigonometry, right? But this guy has multiple things over here going on. So now if we look at it, what are the maximas and minimas here? Take a look. So draw out this graph, and if I ask you what are the maximas, so suppose you're traveling like this, you're traveling from this side, and remember I told you maximas you can look for the hills, right, which you can visually see here, the top of the hills. So clearly we can see that, hey, this qualifies as a maxima. Another hill over here, that's also a maxima. Another hill over here, see at E also. So we are having a maxima at A, and for this value, this is of course the output, the function value at C and at E. Now let's look at the minimas over here, guys. Let's look at the minimas. So do you guys agree this B is a minima? D is another minima. Now the question is, how do we compare these? So you can say, yes, this function is sort of having 3 maxima points, 3 minima points, right? So how do I label them or differentiate them? So why don't all of you draw this graph? So now what names can we give here? See, if we go for this part, see, if you're looking in this area, right? Like normally we say in this area, let's say I'm in Kolkata or in my neighborhood, right? In my neighborhood, in my area, this is the highest, right? Or if I'm standing and looking at a mountain range, right? So if I'm over here in this part, yeah, this looks like a highest point to me. So I can say, because in a neighborhood we'll say, like we say local market, right? We get fruits and vegetables from our local market. I don't go to Delhi to get fruits and vegetables, right? I get it from my area. I don't go to some very far off in Calcutta. So here I can call it a local, right? So within this region, we can say, because it's a local, in this area, this guy is the maximum, local maximum. Similarly, in this area, if you just look at this area and forget about the rest, because in this part, this is the top of the hill. So again, this is a local maxima, point of local maxima, right? Or local maximum, whatever word you want to use there, right? So they use this interchangeably, maxima, maximum, minima, minimum, right? Whatever word you want to use. And this is also another local maxima. Similarly, you guys agree that in this area, this is a local minima, ignoring the others, right? So local minima, same way here, local minima, this point D, okay? So this is one important word, right? Within that area, this is a area of local maxima, not caring about the rest, right? So there it will not matter whether it is an open interval or closed interval, because I'm not just I'm just focusing on this part, right? Looking only at this part. But now if I want to look at the entire thing, right? So if you want to look at the entire thing over here and then say, which is the highest, right? Which is the highest? So suppose, this was a kind of a price graph or a stock price graph, right? You want to see when did the share price go to the highest in this entire day. You guys know the share price, it goes up and down like this, right? So this is another great example, the stock market. So stock market goes up and down. So people get excited. Wow, this stock price right now, at 10 o'clock, it's so much. This might be a local maximum. Maybe it will go higher in the day. Maybe it will go lower. Maybe it will go higher. This is what happens to stock prices. That's a very addictive and exciting and dangerous, right? Because it may rise up and down. So in the entire day, in the stock market, where is the highest value it went? At point C. So we can say that this is the point of absolute maxima, right? So do you guys agree this is a special? C is special. This is the point of absolute maxima. Another word which is used over there, global. Global means, why the word global? because local is for local areas, global means the entire world, right? Or this entire day. Let's say the entire day, this is the highest, global maxima. Now suppose this was the lowest, right? Or maybe we have another part here, but maybe I'll erase this part and not confuse you with this part over here. Okay, so we are going to ignore, let's say we are looking only between, or to make it easy, we can even erase out some further stuff there. Let's say we erase out all that part, right? So if we look at only the, okay, so if we look from this to this, because for global, right, global or basically the absolute maxima or minima. So we talked about the absolute maxima. Here what is the absolute minima? Maybe this value looks a little lower than this. So maybe this becomes your, right? Maybe this becomes your absolute minima, right? D is suppose it looks a little lower than B. So this point again becomes special absolute minima. Okay. And one important thing for absolute, you need to close the interval, right? We have to close the interval to get the absolute, because you want to find, okay, in this entire region, right? So you cannot have endpoints open interval, because again that same problem 0.000, right? Or is it further increasing or decreasing, right? So we have to close it, and this is our absolute maxima, this is the absolute minima. Clear? So this is what, when you read the books, you'll see this kind of terminology use. F is a real valued function. Obviously, we're dealing with real valued function, some interval I, and then you take a point C in that interval. Then it is a local maxima point if in that region. In the region in calculus, how do we define? Remember, we take this H, small quantity, we look in the neighborhood. So at C plus H and C minus H. Like for example, if you consider this point to be C, okay. So guys, consider this point to be C. So here what will this be? This region, let's say this is C plus H, okay, and this part will be to the left of it C minus H. So we are looking to the right of C and left of C, C plus H to C minus H, this part. So when I look over here, this clearly is the point of local maxima. It happens to be global also, but this is the clear point of local maxima. Same thing you can do here, right? C plus H, C minus H, another way, C plus H, C minus H. So in this local area, this is the maxima, another local maxima here. This is what this point is trying to explain you, right? That in this interval from C plus H to C minus H, and here, yes, for local, so one important thing is for local open interval is allowed, right? Because you are not caring for the absolute maxima or minima. So there we say endpoints, we don't care about you, right? It's like, when I'm going shopping, I just care in my neighborhood. I don't care if that neighborhood, the road leads to maybe another market, this road might lead to another market, I don't care. Oh, let those roads be open. I just want to do the shopping in this area, okay? So for that, in the open interval, local maxima, minima, it can be defined, okay? So don't think it's only for closed intervals. In open interval, we can define, and we call that to be the local maximum over there. Similarly, same thing, minimum means, but for all those in that region, this is the highest value. Similarly, this is the lowest value, and of course, we put greater than equal to, suppose there's some slight value, some 2-3 points having the same value, right? But that is greater than or equal to. And same way here, less than or equal to. Main thing is greater than, less than, right? Equal to, again in this open interval, and this is called the local minima, right? This is like our local minima. Clear? So this was the local maxima, this is the local minima. So these are just, I'm connecting the words in the book, right? So that when you pick up the book, you don't say, oh my God, what is this? This is what they're meaning. Open interval, and from to the left and right of it, and this is the highest we got, or this is the lowest we got. Now, we have been all doing it very visually with graphs. Now we are going to come to mathematically, and here again, since we are in calculus land, we are going to use the application of derivatives. Derivatives means doing differentiation, right? So this is very interesting, that how do we apply, because this is in the chapter application of derivative. So how do we calculate maxima, minima using derivatives? Okay, so we are going to be doing the application of derivative, and the key thing I want you to remember, the key thing, derivative means what? You are doing f dash x right? Which is basically you are finding dy by dx. F dash x means what? Dy by dx. And what is f dash x or dy by dx? Remember what it represents graphically? It represents the slope of the graph at that point, correct? F dash x, very important to remember, when you do differentiation or calculate the derivative, you find f dash x, that is representing nothing but the slope of the graph, okay? So let's say you have got this graph over here, right? So this is plotting of y versus x, and this is my graph over here, f of x. We have plotted this graph over here. Let's say this is f of x, right? Now, if you carefully look, if we talk about f dash x, means we are finding the slope. Slope means how do we represent it? So slope you can represent like this. So let's say I want to find the slope at this point. Slope at this point means what? I will draw a tangent. This represents the slope, right? And the angle it meets over here, you can calculate tan theta. Basically, slope means finding the tangent at that point and then extending it here, finding tan theta. That's basically your slope. Or that slope basically means inclination, right? You're finding the slope at this point. Another, if I want to find the slope right at the maximum point, that's my slope. If on this side I want to find the slope, can you see that? This is the meaning. Slope means tangent. So now carefully look at this and tell me that, guys, at the maximum point, the point, let's say C, at C, it got the maximum value. So what is the slope at C, or f dash x is how much at C? Tell me, take a look at the graph carefully and tell me f dash x, the slope of the graph at C looks to be how much? See, at the maximum point, it is the top of the hill. If you look at it, the tangent is parallel to the x-axis. So the slope is going to be, that's right, 0. The slope is 0 here. Look at it. The slope is 0. So this is where at the maxima we know slope is going to be 0. Now if you look to the left of it, on the left hand side, what is this slope looking like? What is this slope looking at? Again, we look at the local part, right? So close to this. Here can you see in this region, f dash x, it's sloping up this way. So can I say, I don't know the value, but I can confidently say that f dash x is greater than 0. Why? Because thing that goes up, when it slopes up like that, it has positive slope, right? So at f dash x here, you can see this is basically your c minus h in this region. On the left hand side, slope is greater than 0. If we go to this right hand side region, c plus h, tell me guys, what does the slope look like? The line is now going down like this, down like this. When you're going down like this, the slope is negative. It will make an obtuse angle if you think in tan theta terms and all. But this you guys know that this is positive slope, this side is negative slope. So this is very interesting, that if you look at this maxima carefully, the maxima is basically this change of slope. Slope changing from positive to 0 to negative. When slope changes from positive to 0 to negative, at that 0 point we have found a maxima. Is that making sense? Right? Of course, under the assumption, sometimes the function is non-differentiable and all. We'll come to there's a special case, right? But if I can find the derivative, if it is a differentiable function, if we can find f dash x, it's very clear that the maxima occurs. So this is my maxima point, and it occurs at, this is the maxima point, or maybe I can mark it down here. This is my maxima point, right? And this is where it happens. Makes sense? Now let's move on to minima. You guys getting the idea? So minima will do the same thing. We can see minima is right here. Now you will get it yourself. This is my minima at C. Take some neighboring points. C plus H, C minus H. You take a look at yourself and tell me, what will be the slope at the minima? Slope means draw the tangent to the curve. So clearly at the minima point, can you see? Can you guys see and tell me? At the minima point, what is it? So at the minima point you can see f dash x is equal to, so right here f dash x is equal to 0. Yeah. If you go to the right side, look at the right side. The slope is like this, and on the left side the slope is like this. See, on the right side it is very clear that the f dash x is greater than 0. See, it's sloping upwards, and here the slope is downwards. F dash x is less than 0. So can you see for your minima what is happening? For minima what is happening? Negative slope to 0 to positive slope. And here it is exactly opposite. Positive slope, 0, negative slope. So this is the logic, this is the application of derivative, where slope of the graph gives you the clue or tells you where is your maxima and minima, and is it a maxima or minima. Here the slope is going from positive 0 to negative maxima, negative 0 to positive minima. So now let's look at this theorem based on the concept we have learned, that if a function is defined in an open interval, this time we are considering an open interval, because we are open interval means you are looking for those local maxima minima. Closed interval means absolute, right? You have fixed it, you have closed the door. So here open interval, and suppose C be any point, right? Then see, open interval means local. See, local maxima or local minima at x equal to C. Then either f dash C is equal to 0, because see, our local maxima and minima happened when the slope is 0. So f dash C means the slope at that point. So f dash x means you have to substitute C, right? F dash C is equal to 0, or there could be another special case that the function is not differentiable at all. Okay, maybe the function is not differentiable, then of course we cannot use that f dash. So there is a special case, and we'll see sometimes that happens, we'll look at that, but this is the more important case, right? And that point is called the critical point. Okay, we call that as the critical point. So right, and we are saying that, so if f is continuous, if your function is continuous, and if f dash C is equal to 0, that means and the function is differentiable, then the function is differentiable, right? And in that interval. So these theorems are given in the book, but basically they are saying that if you're taking this open interval and your function is continuous and f dash C is 0, then obviously it is differentiable, because you have you can find the slope is 0, means you can differentiate it over here, f dash C, and it is differentiable. But the converse may not be true, means it may not be that even if you have this, you may not be able to. So you have to be careful that you may not be able to differentiate the function. So there are special cases like that, but mostly our function will be differentiable, it will be easy. So we'll see that. Like here, let me show you that special cases. So I think it's better to discuss it with the graph example. So suppose here, you can see when our function is curving like this, this is clearly a point of local maxima. You can see this is clearly a point of local maxima, and as we discussed, let's say it's happening at this point C1, here slope is greater than 0, equal to 0, less than 0. Okay, this case also we have discussed, here the slope is less than 0, 0 and greater than 0. Okay, so we have talked about C1 and C2, no problem. Here look at C3. C3 is still a point of local maxima, because if you go, and you check by the function values in this neighborhood, this is clearly the highest, right? It's like if I go in the market and I check the prices, right? Oh, this vendor is giving me the highest price, I will not buy, or this fruit seller is giving me the highest price, next time I will not buy fruits from him, right? So I'm checking, but that I can check, but here I can't use differentiation. Why? Because you can see one slope is going like this, the other slope is going like that. There's a jerk over here. So this function, the point over here is a point of non-differentiability. Okay. So sometimes we cannot apply differentiation if it is not differentiable at that point, but still there could be a point of local maxima. Similarly here, if you look at this point, this is clearly a point of local minima. In this neighborhood, this is the lowest. Like if this vegetable seller is giving me the lowest price, I like it, right? But there may be a discontinuity here in the function. discontinuity, and therefore it is not differentiable. There's a jump, right? So there's no smoothness here. Same way you can see that discontinuity, sudden jerk, and that's why it is not differentiable. So don't think, hey, function is not differentiable means no local maxima minima. No, sometimes we have to see in that region. We have to analyze the function. So there can be certain functions which are non-differentiable but still have a local maxima minima. So that was all these exception cases which were written in a little confusing way. That's why this graph which is given in the NCERT book is a good example for you to understand. Okay, this graph is given in NCERT. Okay, so this has been taken from NCERT. So we saw maxima and minima graphically, right? And this is now we are getting into the real calculus, right? How do we do it analytically, right? So with using derivative. So that's why we call this as the first derivative test. Why first derivative? Because you are just doing one differentiation, dy by dx. We'll talk about a second derivative test also, where you do another differentiation of that, f dash dash x. We'll come to that. Okay. So now let's say you have a function which is defined again, once again, open interval means you're looking for local maxima minimas, right? And the function is nice and continuous at the critical points, okay? And so what is the technique? Remember, first thing you have to find f dash x. Don't work with the function, because we have to work with the slopes. F dash x equal to 0, not fx equal to 0. Don't make that mistake. So that is why your first step is going to be first find f dash x. See, that is our very first step. Step number 2, put f dash x. See, this is the technique. Put f dash x equal to 0, because that is the points of our maxima minima. So if you can differentiate the function, put it equal to 0, right? And whatever values you get, solve for it, you will get some certain points, C1, C2, C3, whatever. And then, now how do you check if it's a maxima or minima? Because note one thing, f dash x equal to 0 doesn't mean maxima. It could be minima also, right? It could be a maxima or a minima. So how will you check? You will check by this logic, right? Is the slope positive, 0 and then negative, or is it negative, 0 and then positive? So this is how you're going to check. So what are you going to do? Look at this carefully, that if f dash x, so basically you look in the neighborhood. So to the left of this, if the slope is positive, right? Remember that graph, remember the graph? We are going here for maximas. So maxima, look at it carefully. At the maxima point, you can see slope is 0. To the left of it, slope is positive. And to the right of it, slope is negative. Can you see that? So slope here positive, slope 0, slope negative. And that is what these lines are writing. See, f dash x greater than 0, positive to the left of ci. Ci means a certain point, C1, C2, whichever one. And then if f dash x is less than 0, right, then to the right of it. So this you have found your point of local maximum. And the next paragraph is exactly the opposite. Look at it. So next paragraph is exactly the opposite. If you have a minima, what did we say? At the minima point, slope is 0. This side, what happens to the slope? Again, not the function, the slope. Here slope is negative and here slope is positive. So at the minima point, you can clearly see f dash x less than 0 to the left of it, right? See, to the left of it, f dash x greater than 0 to the right of it, and this is a point of local minimum. Okay. Similarly here, we were testing greater than 0 to the left and to the right. Now, what happens, this question may arise in your mind, that what happens if we have found f dash x equal to 0, but the sign does not change when you go less than c or greater than c, which means, let's say f dash x remains positive on to the left and to the right, or negative to the left and to the right. That's possible. We'll look at it, right? So it is possible. We'll see that suppose you have some situation like this. Look, if you have some situation like this, and in this region, can you see? So this is very interesting case. Over here the slope is 0. This is the flat line. The slope here is 0. Now if I go to the right of it, look. If we go to the right of it, see, the slope is positive. If you go again to the left of it, slope is once again positive. So both sides slopes is positive. So does not change sign. Fx does not change the sign when you take to the left or to the right. Does not change sign. So this is a special point of inflection, it is called. It is a point of inflection. It is neither a maxima nor a minima, right? It is a point of inflection. So these are the three important cases. So these are the steps you have to do. So this is your case of maxima, minima, and this is your special case, right? Got it? Maxima, minima, and point of inflection. If you visualize this and understand it, it's super easy. But if you're trying to memorize these things, you will not get it. Okay? That's why I've shown you in a very clear graphical way what we are talking about here. And now these sentences which are given in your books also, something like this, it will be very easy. So let's understand with the real example. We have been saying fx. Let's take an actual function. So let's say the function is x cube minus 3x plus 3. And the question is asking, find, see, they have used the word local over here. Find the local maxima and local minima of this function which is given to you. Try it out. So to solve this question, what do we have to do? We have to go for this technique, the first derivative test, right? So see, fx is given. First thing, remember, you have to do dy by dx. You have to find f dash x, right? So come on guys, let's do the first thing. First find the derivative of this function f dash x. X cube's derivative will be what? X to the power n is n x to the power n minus 1. So f dash x will be 3x square. This will become minus 3 and the constant will be 0. So this is the differentiation. Okay. What is the second step, guys? Take a look. It said put f dash x equal to 0 and solve. Not fx, f dash x. So putting f dash x equal to 0, which basically means that 3x square minus 3 equal to 0. Okay. So here I can take the 3 common. So x square minus 1 equal to 0. That means x square equal to 1 means there are two possible options, x equal to plus 1 or x equal to minus 1. That means I'm getting two values where f dash x can be 0. Okay. So now using these two you have to check. Okay. Using these two you have to check. So let's check it, guys. So we'll go to the case 1, or let's go for case 1 where x is equal to plus 1. So it is clear that f dash at 1 it is equal to 0. Okay. But now what did the test say? It says that now you to look to the left of it and right to it, and you have to look not at fx, at f dash x. So don't work with fx, with f dash x. Okay. So now if I say to the left of it, right? So to the left of this point. Left means let's take a value close to 1, maybe we can take 0. So we can say f dash of 0, how much will it be? Let's take a value less than that. So f dash of 0 will be 3 times 0, right? 3 times 0 minus 3. So that's going to be minus 3, which is turning out to be negative. Take a value greater than it to the right side. F dash of, let's take 2. So what will it be? F dash of 2 is how much? 3 times 2 square minus 3, which is basically what? 12 minus 3, 9. So guys, now you decide and tell me that at this point x equal to 1, is it a point of maxima or minima? To the left, f dash x was negative. To the right, f dash x is positive. So what is it? A point of maxima or minima? See, take a look at our criteria. To the left of it, it was negative. To the right, it is positive. So clearly it is a point of minima. Yes or no? So this is exactly how you solve these problems. So simple. So to the left and to the right you check, right? And you can clearly see that. So therefore, so this is a point of minima, or we can say, so x equal to 1. So x equal to 1, it's clearly a point of minima. Correct? It's clearly a point of minima. And what is the minimum value? Just substitute it, right? Just substitute it. Now here you have to substitute in the original function, not in f dash x, right? So here you have to put in the original function, and the fx will be, fx means you have to find f of 1, which is going to be what? 1 cube, 1 minus 3 plus 3. So these two will cancel, right? And we will get 1. So minimum value is 1 and it occurs at x equal to 1. Now let's look at the maximum. Look at the other point. We don't know if it's maximum or minimum. The other point. So what is the other point given to us? X equal to minus 1. So let's work this out at x equal to minus 1. Can you guys do it for me? Come on. Once again, to the left and to the right. Right? So to the left means we can take f dash of minus 1. So take something to the left of it. So or maybe you can take a smaller value, minus half. Right? Something like that. Minus half, or let's say if I take 0, f dash of 0. Ideally we should take in the neighborhood. Right? I'm being a little lazy here. Ideally we should take minus half and minus 3 by 2. Right? And this thing, am I taking the wrong thing? Yeah. To the left of minus 1 means I should take minus 2. Okay, sorry, my mistake. So this should be, because we are doing on the number line, right? So basically here this is the minus 1. So to the left of it I am taking minus 2. To the right of it, let's say I take 0. Okay. So f dash of minus 2 is how much? So again put it in f dash of x. So there you have minus 2 whole square. So minus 2 whole square is 4 times 3, 12. So this will give me 9, which is positive. And this side, if you take to the right of it, if you consider to the right of it, f dash of, this is going to give me how much? F dash of, let's take 0. I think we already found that here. F dash of 0 was minus 3. Negative. Okay. Ideally we should be taking small values, so you should be taking minus half over there, right? So then when we did that positive negative, okay, and you can see that if it is going from, if f dash is moving from positive to negative, it's clearly a point of maxima. Very clear? Okay. So this should be a point of maxima. Make sense? It is a point of maxima, and so then we can say at fx, so point of maxima is x equal to minus 1, and what will be the value? So max value will be f of minus 1. Note that carefully. So I have to put minus 1 into my original formula. So minus 1 cube is minus 1. Minus 1 times that is plus 3 and another plus 3. So I think the maximum value we are getting for this is 5. Is that clear? So very beautiful. This is the way we have to do it. This is the maximum value of the function. Is the steps clear? So you guys can check over here, see. So if you take a look at it, when you look at regions less than 1, right? So you can substitute a sample value, or you will look at the function, right? When you're going less than 1, it's negative, and here it's positive. So whatever way is recommended in your school, but you can put in a value, it's faster, right? Easier that way. So you have to just explore, is it negative, positive, to the left or right, and based on that you decide your minima, like we have decided over here. The minima and the maxima, and also mention the value, right? And value, please remember to put in the original function, not in f dash x. Slope helps you locate the maxima minima, but finally you have to put it in the function to get the final value. Concept is clear? Okay. Now suppose they have given you this kind of question, right? Find the point of local maxima or minima for fx equal to x cube. Can you guys do this for me? So again, see, same thing. Your first step you have to do is find f dash x. So first step you have to do is find f dash x. Always that is the first step here. So differentiation of this is 3x square. Then put f dash x equal to 0. So f dash x equal to 0, which means 3x square equal to 0. So what are we getting? Only option we are getting is x equal to 0. Only one point we are getting, critical. This is our critical point. Now at that critical point, what did he say? Test to the left of it and right to it, right? So to the left of it, the left test I am going to do f dash. Let's take f dash of minus 1, and to the right of 0, f dash of 1. Calculate it for me. So f dash of minus 1, so 3x square is the function. So 3 times 1 square, so this is going to give you 3. And f dash of 1 if you put over here, again you're going to get 3. Both you can see are positive. And you can try for smaller values also, you will get both sides positive, right? So in this neighborhood, see, in fact this is the function here. Maybe I shouldn't have shown this graph to you, but the graph is, this is your x cube function, right? And if you look at it, this is our point where x equal to 0 point, and whether you look in this region, so this is our point sort of C, this is our C plus H, this is our C minus H region, and you can see the slopes are positive. Slopes are positive over here. In both these cases, can you see? Slope is positive. And such a case, remember what was it? This we had covered here. This case is that special case where if the f dash x does not go from positive to negative or negative to positive, does not change sign, it is the point of inflection. So guys, what have you found over here? You have found nothing but the point of inflection. It is neither. So we can say x equal to 0 is a point of inflection. That means therefore no local maxima or minima. Again, see, we are talking about local, right? No local maxima or minima in this region, no, right? And it's an open interval, so I can't say the extreme points. You'll say, what about the extreme points, right? But it's an open interval, so that is why, and it's a point of inflection. Clear? And from the graph also, it's very clear. See, this is clearly not looking like a point of maxima, minima, or maxima. Okay. So for absolute, we have been looking at local. Local, remember, was for the open interval. Absolute is for the closed interval, right? Like I give you that. Close the door and now see who's the tallest and the shortest in the class, right? So absolute maxima and minima. What is the important working rule? Working rule means how do we calculate it? Finally, in the exam, when we are given the question, or if we are given a problem, how do we do it? So this is very important. So suppose first thing again, find all the points where f dash x is equal to 0. This is where the slope was 0, remember? And these were what called the critical points. But there can also be some special points where function is not differentiable, right? We looked at those jerky cases where function is not differentiable. Mostly you will get this smooth kind of case, right, where f dash x is equal to 0. So these are your critical points, and let's say you get one of them or two or more of them. These are your critical points. Now find the fx. So once you have located your critical points, so let's say if you have to find your absolute means global maxima minima, then you don't have to bother doing this left and right test. What is the beauty here about, that's why it's more of a working rule, that straight away once you have found your critical points, directly find the value of the function fx, the value of f at the critical points, and also do it at the end points. So I'll explain you the logic why we are doing this. I'll explain you that, right? So you need to find, so first understand what is the working rule and then let's discuss it. Okay. So basically they are asking you to find the function value at all the critical points and at the extreme points. And now whichever is the greatest value, that becomes your absolute maximum or global maximum. Whichever is your minimum value becomes your absolute minimum. That's it. Okay. So why are they asking us to do this? So like for example, let's take an example over here, that where is this working rule coming from? So very simple again, very simple. So let's take a look at this working rule, that how to find this is for the logic for absolute maximum or minimum, right? Not for the local, for absolute maxima or minima. So what do you have to do over here? So basically, so let's say we have been given a graph. Okay, let's say this is my graph and we are considering this closed interval from A to B, which means the endpoints are included. Okay, endpoints are included. Then what is this working rule telling you? Look at it with the example, it's very simple. It's saying that, hey, and let's say this function is differentiable and all, it's saying that find me all the points where the slope is 0, f dash x equal to 0, the critical points, right? So what will be those points, the critical points where slope is 0? Clearly you can see here slope will be 0. So this C1 will be a critical point. Here also slope is 0. C2 will be a critical point. So does that mean these are the absolute maxima minima? He says, no, don't assume that. Don't assume that. Okay? Don't assume that. Rather, you go for the test all the points. Right? Which points it is asking you to test? C1, C2 and the end points. Don't forget the extreme points A and B. And you'll realize why. Because see, this is a maxima, this is a minima, but at B you can see it takes on a higher value. So this will finally turn out to be the maxima, the global absolute maxima. So this becomes your absolute maxima, and which from this graph it looks like this will become our absolute minima. Suppose that it had gone further down, then that would have been. So question might be arising for you, then why simply f dash x equal to 0 is not working? Why only these where the slope was 0, why aren't these points working? Because see, here the graph is still continuing. So maybe it still hasn't reached its maximum value, right? It is still going on. So that is why we must just check that value as well, because it hasn't turned yet. These are all the turning points, right? When slope is 0 means the graph turns, it becomes its maximum minima, but at that end point it hasn't turned. So we don't know if it is the absolute maxima or minima. Same way here, we don't know if it is the absolute maxima or minima. So the moral of the story is that if you are asked to find the absolute maxima or minima, first of all it will be in a closed interval, and then you better check the critical points. Means you first find out f dash x equal to 0, look at your points, no need to test left, right and all, just directly put in the function values at the critical points and don't forget the extreme points. Okay, then the values, whatever value you get, that will become either your absolute maximum or absolute minimum. Again, to clarify this, let's take a look at an example, because till we do an example we won't get a feel of it. So here you can see I have given you a function 2x cube minus blah 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 on this interval, and first of all notice carefully, it is a closed interval. Can you see the square brackets? It's closed. So first step, what did our working rule say? It said find f dash x. F dash x means differentiated. So 2x cube will give me how much? This will give me 3x square. So multiplied by this 2, so 6x square. So come on, differentiate this for me. 6x square minus, we'll get a 30x plus 36. And what did it say? Set this equal to 0. So put f dash x equal to 0 and solve for the x to get your critical points. So 6x square minus 30x plus 36 equal to 0. So you can divide throughout by 6. I think we'll get x square minus 5x plus 6 equal to 0, which means x minus 2 times x minus 3 equal to 0. So x equal to 2. These guys are my critical points. Do you guys agree? These are our critical points, 2, 3. But since we are looking for the absolute, the global maxima or minima, the working rule says that just don't go for 2, 3, also test out. So your job is to find f of 2, not f dash, f of 2, f of 3 and the extreme points, f of 1 and f of 5. Once you find these points, and see there's no problem, this function was nice and smooth, polynomial function, all differentiable. Once you find these 4 points, you can easily, you'll get the answer, whether it's your maximum or the minimum, right? You'll get the values. So you just have to substitute it. This you can do for me, right? Just plug and play these values and check which is the maximum minimum. So let's see in our solution to save time. So see, at these points, our critical points were what? 2 and 3, and then also the extreme points. See, 1 and 5 are the extreme points. These are our critical points and these are the extreme. Extreme means the end points. Okay, so you substitute it here. See, we are substituting in these values, same thing. So we got f of 1 came out to be 24, this one came out to be 29, f of 3 is 28 and f of 5 is 56. Now you guys can easily clearly see that what is the maximum value there? 56. When it is happening, see, it's happening at an extreme point at x equal to 5. That is your maximum value. And when is the minimum value happening? It is happening at f of 1, 24. Right? So that means these points actually are critical points were local maxima minima. They were not the absolute. They were local maxima minima. These are the absolute. The extreme points are the end points are the absolute maxima minima. Clear? So the working rule is very beautiful. It just says do f dash x equal to 0, find your critical points, and then, so two things, critical points and extreme points. Substitute the values, done. Simple. So basically they'll give you questions like this, they'll just change the, they'll just change the wording. So they're saying find the maximum and minimum, if any, of this function given to you. So they have given you a function. Now how do you find the maximum minimum? So one clue is, are they talking about the absolute one? See, in absolute they should have given an interval, no? Right? Maybe it might turn out to be the absolute, but they have not given us a closed interval. Right? They've just told us this. So maybe this means for all x belongs to R, right? I need to find. So basically here I cannot go for simply the working rule because we don't know the extreme points. We have to go for that first derivative test. So you have to recognize the type of question, right? So here clearly you have to start off first with that option. You have to do f dash x. So this is a square function, so you have to do a derivative of this. So 2 times 2x minus 1, and then again by chain rule differentiate this, so you'll get a multiplied by, or if you differentiate this, you'll get a multiplied by 2 over here and plus 0. So therefore this is my derivative, okay. And if you put this equal to 0, you'll get your critical point. So putting f dash x equal to 0, our critical point is basically turning out to be half. We are getting only one critical point, no problem. So good, less things to test. So now again you have to go for that left hand side, left and right side, right? So you have to check for left and the right, right? So you have to check out, check for, maybe like f dash less than half. So maybe you'll look at f dash 0. Here you'll go to the right side, f dash 1, and you'll check the values, positive or negative. Depending on that, you'll decide. Okay, depending on that. So if you quickly plug in and see, f dash 0 over here is turning out to be what? 0 minus, so clearly negative. You don't even need the exact value. And f dash 1, 2 minus 1, see, clearly positive. We don't need the exact value. So we are going from a negative to a positive, negative to a positive, right? You can visualize that, or you can remember negative, starting with negative means minima. Start with positive, maxima, right? So negative to positive, that means clearly we are dealing with a point of minima. What is the point of minima? That x equal to half. At x equal to half, this function, see, we just got a random function without, so the beauty here is without drawing the graph. Because why? Graph techniques take time, right? Some graphs might be easy. Sometimes, for competitive exams and all, we use graphs, right? There are methods where you can do that. But sometimes, just going by calculus, it's very analytical method. Just follow the steps. Point of minima. What is your point of minima? X equal to half is the point of minima. And what is the minimum value over there? And min value is, how much will it be? So substitute x equal to half into the function. Don't forget that. So if you put x equal to half, I think this terms becomes 0. Minimum value becomes 3. Got it? Got it? Minimum value becomes 3. That's the answer. See, this is the calculus method. Do you want one more shortcut method? Oh, what about the maxima? There is no maxima here, right? We got only one critical point, that's the minimum. There is no maxima. What is the proof of that? So here's another alternative nice shortcut method. Look at this function. So see, start to get a feel of the functions, So another alternative method, even without calculus you can do this. Look at this function. This is a perfect square plus 3. If you look at the function, guys, over here, this function fx, which is 2x minus 1 whole square plus 3, you can see this is a whole square. Whole square means square of a number is always positive, right? Or greater than equal to 0. We can say this term is always greater than equal to 0. And then you are adding a 3 to that. So what is the lowest possible value of this term? 0, 0 or more than 0. So clearly we can see the minimum value. So therefore minimum value is equal to 0 plus 3, which is 3, and max value, no maximum, or basically infinity, right? You can keep putting on bigger values of x, this square will become bigger, no maximum. So we actually didn't need calculus for this, we can do it, right? And we can understand the shape of the graph will be like this, a minima exactly at x equal to half. We even know its value 3. That's why I told you application. We can draw this graph very easily. Got it? So this is how you work with this, and there you can see when we did the test, we got a point of minima. And just by looking at this function, you can see square, perfect square plus 3, no need of calculus. We know that's going to be 3 is the minimum, but there is no maxima. Okay, so there guys, I showed you the alternate method, right? I already showed you the alternate method here, which is basically that this term is positive. So therefore fx minimum value is equal to 3 and no maximum. See, we didn't even get a critical point for the maximum. So absolutely makes sense. Now similarly you may get some more functions, you have got this function, find the maximum and minimum value. Again same procedure. Now it's become very easy, right? So you'll do the same thing, you'll do f dash x, right? So first step is, so basically you have to remember the steps. Find f dash x, okay? So then take f dash x equal to 0. So that will give you the critical points. Got it? You'll get the critical points. Now once you've got the critical points, and see there's no closed interval, so it's not asking for global the absolute maximum or minima. So once again you have to do that testing, right? Less than, greater than. So same procedure. You found your critical point. I think we've got x equal to 1 is the critical point. X equal to 1 is the critical point. See, positive, this is a negative, and this is a point of maxima by using our first derivative test. By the way, you can do this by the alternative method also. Can you see? You can do this by alternative method. Alternatively, what is your method here? What is your method going to be here? Same thing. This is a square number. So just so that you guys are faster, suppose in competitive exam or they give you a MCQ, you don't need a calculus over here. So look at this. So get an intuition for these square functions, they're quite easy, because if you got this, you can clearly see that's going to be positive. This part is going to be always positive. This is always positive, but then you have got a negative in front of that. So basically what do you have? 10 minus this number, 10 minus some number, okay, some positive number here, right? So basically clearly we can see that if you keep increasing this, the function will keep decreasing. So the maximum value can be, because this positive number, the minimum value can be 0. So 10 minus 0, there you go. So therefore maxima is at, this is a positive number, right? So therefore maxima is 10. Done. 10 minus something, that number, it can become very big, it can give you very low values. So in fact no minima, right? It can keep going down and down. But the highest point is when it is equal to 0, so 10. Similarly, if they tell you, find the maxima and minima, you guys can do this. They can call it fx, gx, same old story. You just do the differentiation over there. So this you guys can do for homework, right? X cube plus 1, so differentiation will be 3x square. Now you put 3x square equal to 0. Your inflection point is x equal to 0. And once again you have to do that left and right hand test. But this is a very interesting case, because you will see that on the left side and on the right hand side, you will get both positive. And remember, if the sign doesn't change, it is a point of inflection. So it is that we had seen in x cube, this is only a slight different thing, x cube plus 1. Again, see, if you are getting the feeling of it, that x cube function was going like that, right? You just add a 1 to it, it will make no difference. Again, you will get another point of inflection, it's only shifted. There it was, I think, at 0. Oh, here also it's at 0, right? So, and This one I think if x is less than, it should be less than 0, right? Not 1. So to the left and right of it, when we test it, x less than 0 or greater than 0, we're going to test about the critical point, right? Which is x equal to 0. You will get both positive, so point of inflection. Done. Okay, you guys are all getting the concept? Like for example, this one. Minus, you have mod x plus 1 plus 3. Now mod functions, remember, or even if you take the simple mod function x, the problem with mod function is the modulus function means what? For x positive, give me positive. For negative, give me minus x. You guys remember mod function is, it is equal to x for x greater than equal to 0 and minus x if x is less than 0. So if you guys plot the graph of this guy, its graph is going to look like this, right? Now clearly you can see that it is not differentiable here because there is a jerk, right? So this kind of mod functions, sometimes it's better not to, you can't do f dash x, you can't do the f dash x, not possible here. So g dash x not possible, clearly because the slope is changing with the jerk. So what you can do over here, you just look at the function. Mod means we know it will be positive only, right? Whatever values you put here, this is going to be positive only, and then you're taking a negative of this. So basically you're doing gx, if you think logically, it is negative of a positive number, because this is always, mod is always a very optimistic guy, always positive, right? So negative of a positive number plus 3. Now this positive number guy, positive number will be what? So negative or positive number means a negative number. So basically what are we telling? A negative number or 3 minus a number. Okay. So obviously what will be the maximum or minimum? See, you can start putting big values of x. So this number will start growing. So clearly therefore the maximum value of this or the minimum value of the positive number is 0. So therefore maxima will be gx is equal to 3. When will it happen? When this term is 0. So it will clearly happen when x is minus 1. So this happens clearly at x equal to minus 1. And we can see no minima. No minima, right? No minima. So this one we did again without the calculus differentiation and all. Or another way, see, you can write it like this: gx is always going to be less than equal to 3. So clearly the maximum value is 3. And it will have no minimum value. You can keep going down and down, lower and lower. So we have discussed how to find the maximum minima using first derivative test. We also looked at the working rule for absolute maximum minima, where we talked about, you know, the extreme points. Now let's look at the second derivative test. This is very interesting. So once again, I'll start with the graphical approach so that you get a feel of it, right? What's going on. So suppose this is our function, and let's say this is clearly, it is taking on the maxima over here, right? So at this point C, you can clearly see it is the maxima. So in the first derivative, what did we look at it? For maxima, we were saying f dash x is equal to 0. Okay. When we go to the left of it, to the left side of it, we saw f dash x was what? Greater than 0. Right? When we went to the right of it, we saw f dash x is less than 0. Do you guys agree? So again, you know, thinking in terms of that same thing, C, when you went to the left side, C minus h and C plus h. So now I'll ask you one very interesting question. Now I'll say forget about fx. For a moment, forget about fx. Just focus on f dash x. Okay? F dash x means this slope guy, right? Fx is your graph, which is clearly taking on that hill, the maximum top of the hill there. But I'm saying forget about fx, just look at f dash x. Okay? Now tell me carefully, when you look at f dash x, can you see that f dash x, what is the trend of f dash x? F dash x is going from positive to 0 to negative. Do you guys agree? Can you see? Positive to 0 to negative. That is the trend of f dash x. So can I say f dash x, not fx? F dash x, can you tell me, is it a increasing function or decreasing function? Is f dash x, don't look at fx, look at that first line. Is f dash x an increasing or decreasing function? So let's say it got a slope value of plus 2, right? Then it got 0, then minus 1. So 2, 0, minus 1. Clearly the values are decreasing, yes or no? Right? In fact, you see here high slope, if you go a little further also, high slope, less slope, 0, then negative slope, more negative, right? So clearly f dash x is a decreasing function. Yes or no? F dash x is a decreasing function. Okay? Is that clear? F dash x is a decreasing function. Now we'll pause there and we'll move on to the minima side and see also. For the minima case, which is right here, let's say at C, again we'll look in its neighborhood, like the friendly neighborhood Spider-Man, C plus H and C minus H. And now you guys tell me, what is the trend over here of f dash x once again. So this is my f dash x, and clearly we can see f dash x is 0 here. This side, to the right side, f dash x is positive, greater than 0, and to the left side, slope is negative. That's pretty clear, we have looked at it multiple times, right? So now again I tell you, focus on f dash x. So if you focus on f dash x, in the minima case, first it is negative, then 0, then positive. So f dash x trend is what? Negative, then it goes to 0, then it goes to positive. So guys, can we say that our guy f dash x, our fellow f dash x, is it an increasing or decreasing function? It first takes negative values, then 0, then positive values. So it is clearly an increasing function. F dash x means the slope. Here the slope is not the function fx. Don't look at fx, because fx is increasing and decreasing, right? Here also it is decreasing and increasing. But if you look at f dash x, the slope is clearly an decreasing function here, decreasing. The slope is clearly an increasing function. Yes or no? Now suppose I tell you, find the slope of the slope. I know it's getting crazy, right? Find the slope of the slope. Slope of the slope means double differentiation, double derivative. So can you tell me, now look at it and tell me, and the concept will be clear. If I tell you find the slope of this function, the slope of a decreasing function. So f dash x is a decreasing function. Let's draw the f dash x here. Okay, just as a sample, this is my f dash x, new guy, new kid on the block. F dash x is a decreasing function. F dash x is a decreasing function. So f double dash x, the slope of it will clearly be negative, and you can see that it's going down, right? It's going down. So f double dash x will be less than 0. Yes or no? The derivative of the derivative, which is called double differentiation, that will be less than 0. This is exactly what is the second derivative test. That for maximas, for your maximas, the double differentiation will be less than 0. Similarly, let's move on to the minima side, and the concept will be super clear to you. I promise you guys that here, if you look at it, look at this function, look at the function. We are talking about f dash x, right? F dash x against x. Clearly it is an increasing function, positive to 0 to negative. So maybe it is going something like this, whatever, right? And so here the double differentiation, because it is an increasing function, slope is positive. So this is clearly a point of minima, or a condition for minima. Of course, there's a catch, like, whenever you go for something great, there's a star mark or a catch. Catch is what? That the double differentiation should exist, right? If it is not differentiable again, then you can't do it, right? So the catch is that the double differentiation must exist. This is the maxima, this is the minima. Here f dash x less than 0, there f double dash x greater than 0. So basically, second derivative test says that, hey, now you need to deal with f double dash x. So you need to look not only at f dash x, you need to do one more differentiation, little more hard work, but then it will make life easy for you, f dash dash x, right? So second order derivative of course can be applied if it is differentiable twice, that's your star mark, otherwise you can't differentiate it, otherwise you can't use this test if it is not differentiable, that's our asterisk, right? So let the function be defined on some interval and it be differentiable twice, right? Then you put f dash x equal to 0 to get your critical points, right? So first you are trying to get your critical points, and that was the main problem, right? That we didn't know whether it's a maxima or minima. So what were we doing? We were going around like the friendly neighborhood Spider-Man, checking the left side, the right side. Second derivative says, hey, no need to do all of that. You found your region of maxima or minima. Now I'll tell you, you just differentiate once more. You're a master of differentiation. Differentiate once more and at that point, so at that point of local maxima where you differentiated, if your double differentiation at that critical point, if your double differentiation is less than 0, then it is a point of local maximum. Okay, and then of course fc, you substitute the value, you will get your maximum value. Similarly, if your double differentiation is greater than 0, then it is your point of local minima, right, at that value c. Okay, but if suppose your double differentiation is again equal to 0, then we can't find the maxima or minima, we'll have to go back. So sorry, again another caveat here. So that was the first star mark and this is the second star mark, that life is not always so great, right? This is the second, the conditions apply, these are basically your conditions apply, then you have to go back to your first derivative test. Okay, so this is basically the maths, but this is the logic behind it, that slope is a decreasing function here, so the second derivative is less than 0. Don't get confused, don't say, oh, less than 0 means minima. No, maxima. Here's second derivative, so it's like an opposite. Second derivative, if you get less than 0, you have found your maxima. Second derivative, you've got greater than 0, you have found your minima. And of course, substituting at c, you are putting it equal to, so here I should say f dash, instead of x over here, we need to write c, right, because you are testing at c. So that's basically, it's just a logic, and I've explained you the logic behind this logic, right? Or it's a rule. I've explained you the logic behind the rule. Okay, so that's your second derivative with these two conditions applying, differentiable twice, and suppose you get the double differentiation is giving 0 at that c, sorry, you cannot test whether it's maximum or minima, you have to go for first derivative test. So again, let's understand the rule with an example. So here, suppose this is your function, right? Again, I've taken the similar type of function we have done earlier. So first thing what you have to do, you have to do f dash x. There's no escaping that guy. So we do the differentiation once. So 2 times 2x minus 1 multiplied by 2. So I think we had got 4 times 2x minus 1. Okay. So this is your f dash x, right? And that you will put f dash x equal to 0. So then you can get your critical point, which will be critical point. If you put, you will see the critical point is x equal to half. Then this terms become 0. Then the next thing is you have to take your f double dash x, double differentiation. So if you differentiate this guy again, what will you get? Differentiate it again, you will be left with only ddx of 2x is 2 and times 4, f double dash x is 8. So what did our rule say? If the double differentiation is greater than 0, it is a point of minima. See, and here it doesn't matter whether my x is half, 1, 2, because double differentiation, it sometimes came out to be a constant, which is a positive value. So here you can see this is greater than 0. So f double dash x greater than 0. So this is clearly a point of minima. We have found a point of minima. See, by the first derivative also we got the same answer, second derivative, or by your logic also that, hey, positive number plus 3, so it's a minima. But I've showed you by all the logics we are getting the same thing. Here see, We have got a minima, and clearly you can put the value of x and get, you can see the minimum value will be min value is equal to 3. Put x equal to half over there, you will get 3. Done? Is it clear? Yes or no? Tell me, is it clear? So there you can see, and remember to take the, first get the critical point, then take the double derivative, just making sure that the derivative exists, otherwise you will be in trouble. So there, and it's greater than 0, so point of minimum, and then you substitute the value, and please don't substitute it in first or second derivative in the original function. You will be like, hey, in me, right? Find the max or min in me. Similarly, you can find the max or minimum, same thing, see another function. So same procedure, you have to take f dash x, do the same thing, we had done this example earlier. So take f dash x, whatever you get, then take f double dash x. So here I think if you differentiate, what are you going to get? Minus 2x minus 1 plus 0, and this if you double differentiate, minus 2, so I think we'll get f dash dash x is minus 2. Minus 2 means f double dash x is less than 0, negative. Negative means we have found a point of maxima. See, same answer, you will get exactly the same answer, and maxima will be at x equal to 1, maxima at x equal to 1, and maximum value if you substitute x equal to 1, see max value is 10, which you can very well see from that square logic, but just showing you that second derivative test absolutely holds. And see, we got a negative value, we didn't even have to substitute the critical point. Suppose I had got minus 2x, then don't forget to put, see, at x equal to 1 is the critical point, right? Then you have to put equal to 1. This is important. By chance we are getting a constant. It need not always be a constant. So there you can see this is point of maxima, and that is the maximum value. Done. This is another interesting example. Remember, this one had given us the point of inflection. So see whether you will get it. Try it yourself. So f dash x, nothing difficult. F dash x is 3x square. So x equal to 0 is turning out to be critical point. Now take the double differentiation, f double dash x. See, this time we get something which is having still the x term. So more interesting, right? 6x. Now you have to put at x equal to 0. So right. So f double dash at the critical points. We have only one critical point. So f double dash 0 is turning out to be 6 times 0, which is 0. So now can we say that? So this is basically the problem is here that we are getting. We cannot tell whether this is maxima or minima. Second derivative test fails here, right? So we have to stop here. Can't tell if maxima or minima. So it's like, you know, it's like the snake and ladder game. Go back to the first derivative test, right? So go back to first derivative test. And remember, we had looked at this, or you try it again. More practice the better. That if you look in that neighborhood region, you will see that on the left hand side, right hand side, slope was positive. It was a point of inflection. But second derivative test cannot tell you, right? That later we saw, this one we had seen by the first derivative test. But second derivative test basically tells us no comments. It is neither a point of maximum, or we don't know, right? So you have to go back to your first. That is, that conditions apply. Remember, we had said in that slide, so important. And yes, it might turn out to be a point of inflection, but you cannot comment based on second derivative test. You have to go back. Okay. So there you can see that's what we got. And this last question I'm going to leave you as the homework question, right? So try it out based on what you have learned. So it says, find the local maxima and minima if any of the following using the following function given here. What is the function given to us? It can be fx, gx, whatever, right? Whatever name you want to give, and that is x cube minus 3x. And it says also find the local maximum and minimum values if they exist, right? So now the question comes to your mind that will you use first derivative, second derivative? Since you are learning it new, I would suggest try both methods, right? So try this question out using your first derivative test, or maybe you can go for second derivative if it doesn't work, right? So you try it out. This is going to be this is your homework question. Okay, homework question, and I would suggest try with the first derivative so that the concept is solid to you. First derivative test and the second derivative test which I taught you. Okay, so this is going to be a homework question, and do try it out and let me know your answers in the comments below. I promise to reply to your answers, so go ahead and try out this homework question. And another very important question for you, that which option did you like, the first derivative test or the second derivative test, right? Would you go for the second derivative test, and if it doesn't work, would you then revert back to the first derivative test? Do let me know, because in the next class we are going to discuss the comparison, right, between first derivative test, which one is better, or the second one. Why do we have to go, we saw some reasons why we might have to fall back to the first derivative, but is there any advantage of the first or second derivative test? But I would first like to hear your opinion, and go ahead and try this homework question. Do let me know the answer to the homework question and whether you are in favor of first or second derivative test. Okay, so hope you guys enjoyed this class. So hope you enjoyed this class on maxima and minima, and your confidence now on this topic is at its maxima. So, and don't forget to try out that homework question, and do let me know your answers in the comments, and do check out the courses on our website manochaacademy.com and our Android app Manocha Academy. As you know, we have courses on science, maths, coding, AI, and our IIT NEET Foundation courses. In our courses, you're going to get live classes, concept videos, quizzes, questions, mock tests, and revision notes. So guys, do check it out, do share it out with your friends. Make sure you have subscribed to our YouTube channel. You can follow us on Facebook, Insta, and X. So stay connected with Manocha Academy and just keep on learning.